So let me ask the audience who has already worked with fuzzers and also found many bugs. Great. So which tools were you using? Your own fuzzer? Your own fuzzer? Yes. So that's what we are facing today. A lot of people use their own fuzzers. A lot of people use AFL. So I'm going to dive a little bit into the direction where which approach might be helpful. So going to the agenda today, so we first have a short look and current state of fuzzing, trends and tools, efficiency aspects, coverage-driven versus time-ahead fuzzing, template optimization. Then I show a little project I've set up, going back to more simplified fuzzing setups and evaluate how and what we can achieve with those. Then we go into bug case studies and have a summary and QA. So hopefully we end up at the scheduled time and then meet again for the questions. So, without further ado, so that is me. I've been in IT since peak and pokes with the C64 and ended up with a doctorate about that. No, not about that, but something different. Been into fuzzing since 2010 when I was with Red Hat. I had my first presentation from a totally different topic at Black Hat 2002 and spoke at Hack in the Box at least 3 times. I think 2 times. Now the third time, and the first time was actually over Skype when there was the volcano outbreak in Iceland and I had to do it via remote. In the meantime, I entered the Chromium Security Hall of Fame. I was acknowledged researcher with Microsoft Online Service and F-Secure. I have a day job with researching vulnerabilities in Java at Oracle. So current state, what is fuzzing? Fuzzing is a term which was coined in the 1980s by Barton Miller and his fuzz tool to find faults in command line tools, and he crashed a lot of tools with that. So the technique is to feed a program with semi-random inputs to trigger crashes, errors, or other behavior not defined by the program specification, like hangs also, and things that you would define as undefined behavior. Fuzzing binary with multiple and unexpected inputs allows researchers to discover vulnerabilities, but also functional bugs which may be not specified by the specification. It does not replace, of course, a source audit or vice versa, but both approaches can benefit from each other. Of course, a fool is still a fool with a tool. Fuzzing is as efficient as the tool's use and as ability to cause state transitions between that lead to forward the bug detections. So what different fuzzing technologies are out there? There are mutation-based fuzzing. These fuzzers mutate the input randomly. They do not evaluate the structure of the data or the program. They don't know where the control flow goes. So they just feed random data to the program and test the robustness. And the mutation-based fuzzer can benefit a lot from the user who uses it, for example, giving hints which byte ranges are useful to fuzz, because if you have free text in a document, that's probably less efficient to fuzz than fuzzing the metadata. And if you know what the metadata is, you probably get deeper into the program functionality and can break. Generation-based fuzzers, those are tools that know how the structure of a file or a protocol is made up, and you can make targeted changes from the outset. So doing so promises better coverage. However, there's more management overhead with it because you need to know the setup with a grammar file, or with Peach you have PID files. And detecting coverage also requires instrumentation to be weaved into the target program. So that could be done by on compile time or at runtime. For example, with the QEMO mode of AFL. So, coming to what currently is state of the art. State of the art is the AFL fuzzer written by Michael Zalewski, a security-oriented fuzzer, as being described as a novel type of compile time instrumentation to be used, aims to automatically discover clean, interesting test cases that trigger new internal states in the targeted binary, improving functional coverage for the fuzz code. It's more than just a fuzzer, it's a complete bug discovery optimizer, comes with a POC optimizer, a minimizer, a corporal minimizer, and you have things like a lib dislocator, which exercises the memory management by using edge cases for realloc, for example. It has an optional binary-only instrumentation with QEMO if you want to fuzz binaries as they come from the vendor, or you can use the AFL compilation tools. So it was actually maintained until 2.5.2 by the developer, the initial developer, Mr. Zalewski, but now it's on GitHub, and there are enhanced forks also available, like AFL Smart, which combines AFL with Peach, or AFL++, which is maintained by Marc, and it has a large tool collection and improvements. We can talk hours about AFL, but you can also reach out to the presentation from Adam from DC949 on YouTube, which is very interesting and extensive about AFL. There are also there are also fuzzing tools which are more integrated with development tools like libfuzzer, which is an in-process fuzzer. It has a coverage-guided evolutionary fuzzing engine, and the coverage support is provided by the LLVM framework, which means that the to-be-fuzzed target code is linked with the fuzzing engine. The developer is responsible to write a glue function that links the fuzzing engine to his target. However, with that approach, there come challenges. The target is not supposed to call exit. So if you have a fuzzing campaign and it runs 5,000 test cases, and test case number 3,000 ends up in a state to call exit, your fuzzing campaign is then finished. So you left out the 2,000 remaining cases. In the test case should not change global state, because you are running in one process, and if you change a global variable that causes global behavior change, your test cases are probably not reproducible in all cases. So that works best with small test cases with small control flow, calling into an API, returning, and hoping to cause a crash in between. If you have excessive loops in your target library, that may also be a problem, because you may hit timeouts earlier, which may be incorrectly be attributed as bugs. As with AFL, there's an impressive trophy count, like it has been exercised on many open source projects. You can find a complete description on the LLVM libfuzzer website. In the upcoming flow, we will talk about AFL, because that is better comparable to the approach that I have taken. So OSS Fuzz, that is an overarching fuzzing initiative by Google. It aimed to help open source software more secure and stable. They have a fuzzing farm, a robot army, what they call it, processing 10 trillion test cases a day. So it has builders, and they have fuzzing machines, And these are created using Docker, and the Docker pulls in then the code and the POC templates and exercises the code defined in the Docker file. So there's a list available on the projects, on the OSS Fuzz projects list. What made me look into it was there's no Bison and no Flex, which we'll look into later. So what is, of course, it's great that fuzzing is supported and used regularly by large companies and tools are out there, but it also meant that many researchers switched from their own tools to AFL and libfuzzer because they are the major fuzzing engines used and they want to use these tools too. They potentially spend less time developing their own tools, and it's also more difficult to fine-tune your fuzzing campaign using these tools because they keep the details away from the user. Having everybody running the same mutators in their test cases also means that there is more monoculture in the test cases which are generated and less diversity in what is tested. Less diversity in mutators also lowers the overall probability to find bugs because everybody basically runs the same code path and fine-tuning is difficult. You cannot specify your ranges, or it's more difficult, you have to buy right extensions. The ratio is different to set. It's an internal variable, and coverage-based fuzzing is also used when dump fuzzing would have been sufficient. So if you have shallow bugs, which would have been found by simple mutation fuzzing, you still have the overhead of collecting all the coverage data, choosing which is the best next pass, and all these things, even if the next bug is just one bit flip away. So it's an inefficient, sometimes it's an inefficient use of time and energy resources to generate the coverage data, which is later not used. So that may be a bold statement, so I try to look into what is possible with older tools. Are the bug types that may benefit from typical dump mutation fuzzing patterns? Are there still a lot out there? Is it all fast dry, or do we really need the coverage type fuzzing approaches for all campaigns? While a number of researchers still now use AFL, are there still bugs to be found with dump fuzzing? To answer these, I came up with a little test scenario. So for the project intensely fuzzed with AFL, are there still bugs to be found with non-coverage based fuzzing? So set up two groups of products selected in the AFL trophy case page, for example PHP, and groups, tools that are in a second group, which are not mentioned on any on the trophy case pages, like Flex or Bison. Then I ran dump fuzzing campaigns on these tools and triaged the bugs that came out. So, which tools came into use? That was first the ZUF fuzzer from Sam Hookevar, version 015 was used. It's a transparent application input fuzzer. So it's like a pipe. You pipe a set of bytes to it and it does random bit flipping, and on the other side of the pipe there comes out the fuzzed version of it. Depending on the seed, depending on the ratio. There's also an advanced mutation-based fuzzer, which is Radamsa from Finland, and it's a general-purpose fuzzer for all kinds of data. The goal is to find issues that cause the program to misbehave. So it uses very kinds of heuristic and change patterns, inserting bits, bytes. It has an XML mode. Sometimes it has bit flips. So it randomly uses this particular mutator based on the current seed. So I also had a little fuzzing farm, one MacBook Pro running Mojave and Docker, CentOS 7.7 and Ubuntu 18.04 in the Docker engines. One old Athlon I used. Can I use it still? So that was about $400 when I bought it. And a Lenovo Intel desktop. So that was my answer to the Google fuzzing farm. The campaign time frame was September until actually yesterday, where I received an answer from the Git team. And I used a couple of shell scripts, the Radamsa Zuf tool, and Python to create advanced POC templates. So what were my friendly little helpers along the way? Malloc check and guard malloc to have something that runs with checks the memory behavior. I used CodeSign to work around integrity protection on macOS binaries, and some fancy little shell scripts for better tool integration, like getting into LLDB, getting out, and running batch for isolated test triage. So there was a standard test harness I used. I used a shell script with the trap catcher, and everything ran into loop, and then that's how simple it was. I ran ZZUF in the loop and collected the crashes. But the answer was and the same for Radamsa, and the answer was still, does this simple setup still find bugs? Is there something, was AFL so successful that it made simple crashes being dried out? So what was presented in the last few slides, a simple harness that wraps ZZUF Radamsa. We are fuzzing binaries as is to prevent Heisenbugs. So Heisenbugs means are these bugs introduced by the testing framework itself. We use a minimal test memory sanity check, install traps to catch and collect mutators that causes these crashes, and log these crashes with a time stamp. Then run the mutator, triage the results, and report any bugs to the vendor, optionally. So, starting with fuzzing grammars. Mutation-based fuzzing with grammar templates seems to be less successful. There are no many bug reports on these tools. But how can we mix smart template data with dumb fuzzing? So let's start choosing a target with a large user base. Since the old Unix days, there is the Lex Yak, as it was called, combo, which on the GNU world is Flex Bison. Flex is a fast lexical analyzer, and Bison is a general purpose parser generator that converts grammar into C code, a working parser. So these both tools were not mentioned on the AFL or lib fuzzer trouble case, so that was a nice thing to try. So Flex is, as being said, the fast lexical analyzer. Takes rules and converts these rules to a C code, and we try to find if that causes actual crashes. So our input corpus was composed of text files containing both text and metadata. Flex forwards parts of the input directly to the output, so fuzzing those areas inefficient. So when creating test files, keep those files with as less free text as possible and use as much metadata and control instructions to have a high metadata to text ratio to cause as much functionality being hit as possible. Bit and byte mutation is not likely to cause exceptional parser states on a broader scale. So Radamza was used as tool of the choice here because it was possible to break out of syntaxes and multiply parts of the input. So there were some exceptional states to be expected. Zof, on the other hand, was useful if a given byte range was supposed to be fuzzed. For example, if a flex input file, they have some regex areas, and if you hit a nice bit combination with a bit mutation, there could be something to be found. So let's look into the first flex crash case discovered, which was a realloc case. So this was discovered on CentOS using Radamza. And after a while we hit a realloc bug in Flex, just because of this larger regex. So with this regex, it caused reallocs being created and executed, but on pointers which had old sizes. So that was first not identifiable where it was could be found. So it was not in the Flex debug info, so we had to install GCC base debug info 2. So after that was then fixed, a bug was found in SF pushed, and as being tested, that was also causing a crash in the Xcode version of Flex when you were using guard mallocs. Looking into CentOS 7 code, it came out that it is missing a backport of a defense in depth fix that was introduced in 2.6.4, which you can find on GitHub. And actually it uses the guard to prevent this issue. So a second bug was found in a free condition. So there was a memory block being freed which wasn't used before. So how was that detected? It was detected in the DCG get text function, which has a known vulnerability in that area, and obviously the new code does not call directly there. So that was our approach. Also, as comparison, AFL was used, and AFL spent a lot of time actually finding nothing, and after 6 hours we abandoned this test. So AFL mutation strategies do not seem to get to the point so early. Does not seem to lead sufficient complexity to create enough complexity to create these tests, these conditions, such as creating a grammar definition with sufficiently dangerous recursion, as in the first case. So it looks like the combination of a complex base template plus Radamza mutation has speed advantage here. So that was GNU Flex. Coming to GNU Bison. GNU Bison is a parser generator also of the GNU project. It reads a specification of context-free grammar, blah, 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 and you see how the grammar looks like. This is a simple and otherwise useless example, but to fit on the stage, that is something that my grammar Python tool creates as test case. So when you run that with on Python 3.04, you get a heap corruption in LLR, build relations, and it also has, so this causes a double free. As the edge thing was freed too often. So avoid, how was the test case created? To create, how could we call into this, create this scenario where the double free was triggered? So again, we have we don't have much free text in this generator. This generator creates as much control structures as possible and does, for example, you can do this by using simple Python, and then you have the grammar which is here on the first introduction page. So no free text, just control for. So using this reproducer allowed to create a fuzz case which had unexpected EOF, and this unexpected EOF would cause crashes on Python, and the process would abort. So this was fixed relatively quick by the Python project. Also there's an EOF issue which could also cause a DOS with these tokens being repeated. So also this could be used if you supply a Python file to an unaware developer that his build chain might not complete and not build the product, which could be used for sabotaging software pipelines. So as you see, there are fixes from the Python project, but there are no fixes from the Flex project. So haven't seen an answer till today. So again, Python and AFL, this went for 3 days and eventually ran out of memory, but no finding with the same test data. So here, AFL mutation strategies do not lead towards sufficiently complex complexity to break Python. So there probably was no grammar that came out that was sufficiently dangerous to cause a crash. So here again, Radamza plus Python has a slight speed advantage. So that were the tools that we checked that were not in the trophy case of AFL and libfuzzer. So now we have 2 trophies here. More findings, C++ filter. The C++ filter is it's a tool to apply the inverse mangling of C++ names by decoding low-level names into user-level names so they can be read. So no findings in reasonable time with AFL on CPP field. But using Radamza, there were 3 issues found. We present one here, and it's affecting CentOS and OS X versions of C++ field. So we have, actually we have 2. So we have this memory allocation. So we have this 20 bytes, and these 20 bytes cause memory allocation of this unpronounceable byte block size. So that's how you can test your virtual memory manager with C++ field. And another invalid read in C++ field, if you have if you have if you have an input that starts with _z, you get into an invalid read scenario, demangling the C++ template, and you see here that that is a specific case and that the mangled pointer is invalid, and you cannot read from that. This third issue with C++ filled is that it may run forever. There's an endless loop and a parent endless loop. At least it was then killed by the processor, by the system after 10 minutes. So if you add some unnoticeable C++ filled instruction to a make file, it may then run forever. There's also a problem with the Git. So there's on the user side, not on the server side, because you build these indexes on the user side when you clone the repository, but still it's a little bit annoying. So Git is a free and open source distributed version control system designed to handle everything from small to very large projects in speed and efficiency. It keeps information about transition between the commit states in metadata index in the Git directory. So what can be mutated in this area? So this is mostly binary data, so we flip bits with ZUF. So result was Git does not properly validate the metadata before access and causes Git segmentation fault in the cache handling code up to the newest version. It was first reported to Apple Product Security because it was due to actually there were two test cases, but both landing in the same code. So first the one from Apple was found, so Apple Product Security was informed, but there was no response till today. Git security team ruled out that it would be directly exploitable, but still a potential vector to sabotage developer productivity. It was not fussed with AFL, but it is mentioned on the AFL trophy case page, so there is actually bugs being found with AFL and Git. So this is the crash location. You see if you have Git repository, and the Git repository has manipulated index files. You get into this loop cache and you access memory which is out of bounds, and then you get this bad access. So some fun to play with Git. Coming to GNU Make. GNU Make is a tool which controls the generation of executables and source code files of the program, and it creates a pipeline of actions and dependencies, and in the beginning you have your source code, and in the end you hopefully have your executable binary. So the input file which led to this finding was ironically the AFL make file, and we used Redenza to turn this file into a reproducer that causes this stack exhaustion. So that was reported to the GNU maintainer, who acknowledged the report, said it would probably be difficult to implement a recursion depth limit in the near future, but he also sees no urge to do that quickly. So where does the stack exhaustion occur? It occurs in the for each construct of GNU Make. So if you have nested for eaches, the stack runs out of what is available. So here you see it better. Here this project that will be evaluated, then you have the nested for each, and the nested for each then causes realloc, and the realloc is triggered for each frame, and then you run out of stack space. And they also use alloc A, which is also not that fine code construction, but as the developer said, it's the only feasible approach they can take there. So this is not yet fixed, but also according to the make project, not a big threat. Coming to PHP, PHP is a general purpose scripting language that is especially suited to web development, and an input corpus was created with nested object structures that caused a stack overflow during unserialization. So we created a Python script and fuzzed that output later with Verdanza. And we have seen that AFL was previously used to report similar issues in PHP. So we reported that to the PHP privately where the security address. They were triaging that for 5 minutes that it was not a security bug because unserialization bugs are generally not security bugs. Okay. However, after filing a public bug, a fix was available very fast, and also there was a hardening fix following to enforce a recursion depth. That would no longer hit the hardware stack size. Supposedly that was also found by OSS Fuzz, but these bug reports are still embargoed, which indicates that the bug somehow may be still security relevant. And also the OSS bug numbers are still were filed after our report and are still closed. So here we see the stack trace of PHP 7.3.9 by that time, and we see that the bug triggers recursive frames of process nested data. How does the payload look like? How was it constructed? The base complexity of the POC was used using a Python script. So we used a typical small serialized Python object and replaced the element part by a more complex thing, and that was done with a recursion, and we ended up with arbitrary large object trees. So how was that fixed? There's an upcoming default patch for PHP, and it adds a max depth option to unserialized, so at least our bug had some effect on the PHP default security. Coming to the bugs that are being filed by OSS Fuzz, they are not open yet, but probably similar to what we reported. Another thing was XPDF. We found an invalid read in the catalog destructor. I think that was made public 2 weeks ago. That was found by the implementation fuzzing, and the root cause is that the catalog destructor destroys data too early, and there's still an access, and then it crashes. We found an additional bug, so there are no details yet. There's an endless loop due to an embargoed reason. Maybe in updated slides this will be filled. Free type, there was a bug in OT valid. Well, use the validation code to verify that that your data is valid and free from malicious something embedded. But here the validation code crashed, and because there was a missing guarding check. So this was being reported to FreeType, and you see the RAX register is somehow seemed to be an underflow, and the OT valid was fixed with this patch. There was an additional bug in ftdump. ftdump was not verifying length fields. I forgot, this was found with ZZUF. Sorry, that's not on the slide. Also, this was found with ZZUF, and here we see that the dump tool of FreeType utils does not verify length fields, and they also came out very fast with a fix. So we don't have here the 2-hour version, we have the 1-hour version, so this is left out here: JQ, Poplar, BinUtil, CTEX, Ghostweb, SQLite, and XFS. And due to time being advanced, we come to the summary. So what is the summary of that? Coverage-based fuzzers are impressive tools, but don't waste them on easy targets. Fuzzing not driven by coverage can still allow harvesting interesting bugs. Observe when starting with input corpora that has efficient complexity, but that provides the tester to have some insights of the structure and behavior of the software project. Do not go away from coverage-based fuzzing, but first get rid of the shallow bugs you can find with easier fuzzers. Then your coverage data also has much more value because you don't have to waste your resources and on the easy bugs, which you can eliminate earlier. So the proposed staged workflow is to dividing your fuzzing resources, is to spending expensive resources, not to spend spending resources for the shallow bugs, which can be found even without coverage data. So dividing by resources, reserve machines for simple mutation fuzzing, others for AFL. Or if you divide it by time, you can take for advantage that you first get rid of the easy bugs, and then start fuzzing the code with coverage-based fuzzing, and also have more and better coverage information about the cleaner code. And you can parallelly fix your bugs and then still fuzz in the other campaign. So finally, and Q&A. And for ideas and comments, you can contact me via this email address, and I'd like to thank you for your attention. So, we have questions? Not so many today. Was there a question? No?
Then I thank you for this very informative presentation, Marc.
Thank you
very much. Give him one more big applause.
Yeah.
There was a question, actually.
Yeah.
Yesterday I attended the hacking class for a vehicle.
Mm-hmm.
So what's the difference if it's a Tesla or it's a, how can hackers like hack a car but they're at their home and they can break out your car system?
Cars are also computers, and cars come with open source components like the ones I presented here. So if you know vulnerabilities in these car software systems, you can, if you know a known vulnerability or these cars have outdated vulnerabilities, you can break them as simple as you would break a desktop software system. Of course, you need to know which input paths of data are there, but if you have a path from to the computer that's in the car, it behaves as as a normal computer. Or if you have your car with a media system, that's even easier. You have your USB stick, the car has a software stack to read USB drives, and then the car uses then your USB drive, your file system is manipulated, has a payload, the payload manipulates the car USB stack, the car USB stack propagates to the car kernel, simplifiedly said, but you need to do some island hopping. First make this your base, then hop to the next base, have the next exploit for the next phase. So you need to know all these little vulnerabilities on the way from your unprivileged state to what the car privileged operating system does. But that's not that different from other computers.
Thank you.
Thank you. Yeah. And now we are hungry.
I thank you once more, Marc.
Yeah, thanks.
Thank you.